Hello students, I hope you all are fine. Today we are going to start with our new chapter, that is electromagnetic induction. Electromagnetic induction, that is EMI. Okay. So before moving towards that chapter, you need to understand one topic, that is magnetic flux. Magnetic flux is same as the electric flux. Here only the change is, instead of electric field it is magnetic field. I hope you all remember what was electric flux. If you are not remembering, just go back to your first chapter, revise it. And if you are not still getting it, you can understand it over here also. So what is a flux? Flux is a number of field lines passing through a surface. Suppose this is a surface, then the number of field lines passing through this surface is known as flux. Generally it is denoted by phi. Here we are talking about magnetic flux, that why we will be using phi b. Okay. So what is magnetic flux? Number of field lines passing perpendicularly through the surface. Suppose if I have a surface over here, and if I apply, keep it in an external magnetic field. Suppose this is a magnetic field. Then the flux, this is the magnetic field. Instead, here in electric flux it was electric field. Here in magnetic flux it is magnetic field. So suppose if I want to find the flux from it, then the flux in this magnetic field will be equal to phi b, that will be equals to, how many field lines are passing through the surface? 1 and 2. Only 2 field lines are passing through this surface. So the magnetic flux will be equals to 2. Now on what does this depend? For this will take few conditions. If I increase the intensity of this magnetic field, what will happen? The field lines will get closer. Suppose here if I again have the same area, okay, I am having a same area, the surface with same area, but what I have done, I am increasing the intensity of this magnetic field. So the number of field lines will increase. We all know that the number of field lines increases as we increase the magnetic intensity. So here, what will be the number of field lines passing? It will be 1, 2 and 3, which means that phi b will be equals to 3, which tells us that flux is directly proportional to the intensity of magnetic field. Flux is directly proportional to intensity of magnetic field. As we increase the magnetic field, the flux increases. If we decrease the magnetic field, then the flux again decreases. Okay. Now instead of this, what I will do, for the same magnetic field, if I increase the area, this surface area of this surface, if I increase the area, then what will happen? Here you can see I have increased the area. If I am having the same magnetic field, what will happen? The number of field lines passing through it will obviously increase. The number of field lines passing through it will obviously increase as the area is increased. If I increase the area here only, if I get a bigger area, what will be the flux? The number of field lines passing through the bigger area will increase. So for bigger area, the flux will be 1, 2, 3, 4 and 5, because all the field lines are passing through it. Here also you can see 1, 2, 3, 4 and 5. You can get, as the area increases, the number of field lines passing through that surface also increases, which means that flux increases. For bigger one, the flux will be equals to 5, which tells us that flux is directly proportional to area also. Flux is proportional to magnetic field intensity and flux is proportional to area also. So I can write this in the form of phi b is equals to b dot a. Suppose the proportionality constant is equals to 1, then can I write it in this form? It is dot product of b and a. If b increases or a increases, the value of flux will increase. Okay. So if I want to remove this dot product, can I write it in the form of b a cos theta? B a cos theta. This is the formula for flux. Now I will make you understand that it depends on cos theta also, but let it be. What is the formula for flux? That is B a cos theta. Now how it you already studied, it depends on magnetic field and area. Now we'll study about how it depends on the theta, that is cos theta. So for that, okay, it is not always necessary that magnetic field is always in the straight line. it can be inclined also, it can be above also, it can be in any direction. So suppose we take an area. We are having a surface area. Area vector is always perpendicular to that surface. So this will be our area vector. Now suppose this time the magnetic field line, instead of going in this direction, are in this way. Okay, this is the magnetic field intensity. So what will this angle will be? Theta. Let us take that this angle is theta. But here our condition is number of field line passing perpendicular to the surface. Is this passing perpendicularly? No, it is making some angle theta. So what we'll do? We'll take two components of this. One will be in this direction and one will be in this direction. This will be B sin theta and this one will be B cos theta. These are two components of magnetic field, which means that here we can see that now B cos theta is passing perpendicularly, or you can say in the direction of area vector, that is traveling perpendicularly to the surface. So we can know that it depends on cos theta, that it is BA cos theta. Okay, if anyone wants to understand this also, then here let us understand the angle between these two components is 90 degree, that is the angle between area vector and B vector, that is 90 degree. So if I put the value of 90 over here, what it will be? Phi is equals to BA cos 90. Cos 90 is 0, which means that flux is 0. To understand this, let us see that this is the vertical vector, or you can say B sin theta vector component of B, and this is the surface. So what will happen? It will directly pass on from here. It will not pass through the surface. It will pass only from near to the surface. So it will not create any flux. The flux is created only due to this B cos component. So from that we can say that the formula for flux is equals to B A cos theta. B A cos theta. So if you want to know whether this is a scalar quantity or vector quantity, it is directly from here we can say that it is a dot product, and dot product itself says that it is a scalar product of two scalar things, or scalar product is dot. So which means that this is a scalar product. Phi or flux is a scalar product. If it would have been a cross or a cross product, then it would be a vector product, but here it is a dot product, that's why it is a scalar component, or you can say scalar quantity. Now if you want to talk about the unit of it, unit of phi equals to BA, unit of B is Tesla and unit of A is meter square. So this will be your Tesla, meter square will be your SI unit, or you can also say it as Weber. Weber is also used as a unit for magnetic flux. Okay, I hope this whole phenomena or the whole concept of magnetic flux is very clear to you, because it will be very useful for the further lectures to come. So keep studying till then. Study this. If you have not studied this, just refer to the first chapter also. You can correlate the electric flux with your magnetic flux also. Okay students, thank you. Have a nice day.